to integrable systems. So, which I think is what interests most of you. This is the outline. So first, I want to tell you a bit about quantum quenches and one-dimensional Bose-Gaussian experiments. And then the rest of the talk, which is essentially the main content, is going to be divided in two pieces. The first one deals with quenches to integrable systems that can be mapped to non-interacting ones, and that's what I call, so sometimes people call them like non-interacting, and that's why I put quotations, because I'm going to argue that even if you can map them to non-interacting models, those integrable systems are fundamentally different from non-interacting ones. And the second part deals with quenches to integrable systems that cannot be mapped to non-interacting ones. And they are what I want to argue, that those quenches are really fundamentally different from quenches to non-integrable systems. Okay, so, and then the summary. Okay, so let's start with the experiments. This quantum quench, I think most of you are familiar with the term, but let me just tell it to the rest of you that may not know about it. It's a protocol we use to take systems far from equilibrium. Okay, so we have some system in equilibrium under some condition. It could be the ground state of some Hamiltonian, and then we change some parameters suddenly. Okay, now this maybe is not that familiar to condensed matter physicists, but it's actually very familiar to cold atoms experimentalists. Now, let me tell you, there have been many quantum quenches. Okay, so I'm going to describe an experiment which interpretation I was involved with that that makes that point of the quench very clear. Okay, so, and this was an experiment done by Sebastian Will, who's a former graduate student of Immanuel Bloch. So what they did is they created three-dimensional Bose-Einstein condensate coexisting with a three-dimensional Fermi sea. So to a very good approximation, you can think the gas is very dilute, so you have non-interacting fermions and non-interacting bosons all living together in some lattice. Okay, so that's the initial equilibrium state, and then what they did in the experiment is suddenly ramp the lattice depth to be something that is very deep. So essentially to a point in which fermions and bosons are trapped on the lattice size. They almost cannot move around. Okay. Now you say like, okay, what happens after that? Well, you may think nothing happens, right? Because the bosons and the fermions cannot move around. And indeed, nothing happens to the density. But correlation functions do evolve with time, and you can see that very quickly by just solving a very simple two-side problem. And so long as there are fermions in these two sides, or they are initially correlated, and there are different number of bosons in the side, this correlation function is going to change with time. Okay, so that's just a very simple calculation. Now the beauty of these experiments, or just the idealized theoretical version of it, is that it can be solved exactly. So essentially, if you have a non-interacting BEC and you think the initial state is just a direct product with a Fermi sea, you can actually trace out the bosons and look at the dynamics of the fermion. So now we can do that exactly in one dimension for any filling, and in higher dimension at low filling, so that you have spherical Fermi surfaces. So this is the answer for one dimension, let's say. So you see this depends on time. So this part in here is what you know how correlations function behave in equilibrium, and now you see what the bosons do. So essentially, as you depart from time zero, the time of the quench, what you see is that these correlations are exponentially suppressed in time. Up to, you get to some later time, which is the period, and at that time, then they go back to the original ones, okay?
They also are coupled together?
They are coupled by the interaction, the on-site interaction, this UBF. Okay, so which is, you just did the wells very deep. Initially, this UBF was very small because the wells were not deep. Then you made it very deep, and then that UBF is final. Okay, so now this is the analytic expression. This is how it looks. Actually, if you plot it at T0, this is how correlations look in the ground state of fermions, non-interacting fermions. So as time moved from zero, this point stopped there, okay? And then you see the correlations start to decay, and at half the period, they are essentially flat. Okay, now if you look at that in momentum space, it's amazing, because what that tells you is that you start with a Fermi sea, and then at half a period, then it's become flat. And then you wait a full period, it's come back to a full Fermi sea, and then you have like a collapse and revival of that Fermi sea. Okay, so Now, what happens with the experiment? So before I show you the experimental results, and you are a bit disappointed, then let me tell you a bit about the experiments. So you see, all that I solved there was homogeneous system, everything beautiful and simplified, but in the experiments, because of the Fermi pressure, the Fermi gas is much larger than, the Fermi cloud is much larger than the boson cloud. On top of that, because of the gravitational field, they had some displacement. So everything I told you happened in this little piece of the fermionic cloud. Okay, so the system is inhomogeneous and so on. But nevertheless, if you look at this is like a picture of the fermionic momentum distribution function taken after time of flight. What we do is just to make things simple, integrate along the direction of gravity, and then you get these plots. And what you see is at different times, these momentum distribution functions are different. Okay, now they are not squares like you would expect, and they don't go from 0 to something that is non-zero, but you can see the difference. If you plot it now as a function of time, then it's beautiful because you see that there are these oscillations, and the period is precisely this period. Okay, so essentially that shows that in these experiments out there, to have this very long coherence time, you see you need to have something that is very well isolated from the environment. So the problem we solve is just unitary evolution, and then it's very similar to what you have in the experiment. And for them, it's just very natural to have this quantum quench and follow the dynamics. Okay, so this was in a three-dimensional lattice. So, I mean, many people here are interested in integrable systems. So in a way, that system I showed was integrable. So, but more generic integrable systems, you will get them in one dimension. And in the experiments, they can create them using two-dimensional lattices. And at very low temperature, essentially, the interaction between bosons can be written in this way, in which now the experimentalists, they can control this effective strength by just changing the intensity of the laser light. Okay? And then they can do beautiful things, so like in equilibrium, they can measure like what is called this G2 correlation. It's a local correlation. And like the experimental point, they can, as I said, they can change this G, they can also change the density. This is the gamma effect, if you know, from the Liebling model. And essentially, they can measure this G2 as a function of this gamma effective. In this case, they just change the density. And these are the experimental points. And then the line is really the theoretical prediction using the Liebling model. Okay, so you see that, that in this case, we have an exact solution that now can be essentially matched by an experiment. Okay, so this is in equilibrium, and similar to the case before, they can take them far from equilibrium, and this is probably the experiment that got most of us thinking about these problems of thermalization, in which what they did is they took these 1D gases, they applied light, they laser pulses, took them far from equilibrium, and then at long time, they measured the momentum distribution function for different values of gamma. And what they get is that, I mean, they are in a harmonic trap, is that after a long time, this momentum distribution function have these peaks. And then these peaks essentially tell you that this cannot be a thermal equilibrium momentum distribution. And this was very strong gamma. And as they go to the lowest gamma, in which the system still remains one-dimensional, still they get a distribution. You could think, oh, it looks thermal, but actually the thermal prediction is this dashed line. So it was never thermal. And this has been, seen. There are other experiments and so on.
Thermal, you mean Gaussian?
By thermal, I mean thermal. So you have to really calculate because this is interacting and it depends on the temperature and so on. Okay. So essentially, these are the capabilities experiments have. So essentially, if you can come up with some experiment to see something interesting, I mean, they could potentially do it. Okay.
So the equilibrium is the Bethe-Ansel solution.
The equilibrium is it's like a Bethe-Ansel solution. Right. Okay. So questions on the experiments? Okay. So now, I mean, to try to understand that, I mean, it was not obvious at the beginning why is it that that these things were not thermal. I mean, it helped a lot in understanding these experiments just to deal with very simple integrable models that could be mapped to non-interacting ones. And one of those models are hardcore bosons. And to make things even simpler, I mean, when we started thinking about this, we put them on a lattice. It's just so much easy to deal with. And the nice thing is that we can solve those hardcore boson models in arbitrary potentials. Okay, and the way we do that, well, you see, it looks like they are not interacting, but there is this constraint on the creation annihilation operators. You cannot have more than one boson per site. And the nice thing about this model is that you can map it to spin and then spin to fermions using this Jordan linear transformation. So, and then essentially you can diagonalize this quadratic Hamiltonian. Okay, now this mapping immediately gave us something for free, which were some conserved quantities. I mean, so there were non-trivial things that were conserved during the dynamics, and those were the occupation of these fermionic modes, of the eigenstate of the fermions, okay? Because these fermions are non-interacting. So, and I mean, at that time, then we thought like, okay, so now if you try to maximize, so if you try to get what is the maximal entropy subject to this constraint, what you get is like a new ensemble, okay? And then here you have these conserved quantities, and you also get the Lagrange multipliers that you can calculate analytically just from the initial state. Okay, so that was all very naive at that time. So now, okay, so now obviously we are interested in other things that are not fermionic correlations. So we are interested in, like, for example, momentum distribution function of the bosons. And for that, you need to compute off-diagonal correlations. Okay, and those ones are more complicated because when you write in terms of fermions, then you get all these strings in here. And on top of that, you have to also compute the time evolution of that fermionic system. And here, I think like Slater determinants are very helpful. So because the evolution of a Slater determinant, the time evolution is a new Slater determinant. And the same you can apply, and this is just, one can easily show that it's just the action of a bilinear form in creation annihilation operators. In fermionic, fermions acting as Slater determinant gives you a new Slater determinant. And you see that this is bilinear. So ultimately what you have is to compute some green function in some Slater determinant, okay? And this can be done very efficiently. It ends up being a product, is a determinant of a product of two matrices. Okay, so we can calculate that in polynomial time to get arbitrary long time evolutions. So, and the other thing that you need to be able to do is the thermal prediction, and that we do in the grand canonical ensemble. And the same for the GGE, and I mean, all these can be generalized, and now the only thing is that the calculation time scales with the linear dimension to the fifth. Okay, so that's like my lab. So that's all I need to do my experiments. I can do the dynamics, and I can calculate the thermal predictions and the GGE. So, and now let's see somehow a cleaner version of the experiment. So what I'm going to show you here is what happens if you have just a big lattice, okay, and you add a new lattice to it. So, and then essentially we start with the ground state. So this is the density initially. So remember, we have, and that's why we call it a super lattice. So you can think of this as having a lattice with a longer lattice. And we do it at very low density so that you could even think of this as you having some continuous system with an additional lattice. Okay, so what happens in the momentum distribution function is now that in addition to this k equals 0 peak that one usually have for bosons, now we have other replicas of that are related to this new lattice that we introduced. Okay, and then we turn off the lattice. Okay, so we look at the dynamics. Now, what should happen to this system if it thermalizes? Let's try to think about that. What should happen is just that you should get in the end just one peak, right? Because at the end there is no additional lattice there, and the thermal prediction would be just some broader peak. Okay, so but let's see what the dynamics does. So this is the real time evolution. This time scale here is h bar over j. Okay, is the time scale associated with the hopping. Okay, and what you see is that after long times, the evolution of the density you can calculate it analytically. It's the same as free fermions. It just goes polynomially to some like the average. But the amazing thing is what happens in the momentum distribution function, right? So what you see is that it started with very high peaks, but it relaxed to a distribution in which you still have peaks, okay? And it doesn't change with time. So essentially the system at long time remembers that, that it was coming from that initial state and it's not thermal, okay? So, and then we say like, okay, we understand why the experiments were giving something that, that was looking not thermal. The other thing that we can do then is calculate this generalized Gibbs ensemble prediction, and then for the density you get that it's flat, which is what you will get in here at very long time. And for the momentum distribution function, you perfectly reproduce all the peaks. Okay, so at this point then, we also have a way to understand what the long time behavior is. Okay. So now, I mean, you could just stop here and then do some other things, but at that point we started thinking like, why is it that this GGE works? Okay, because I just maximize the entropy. I mean, why will that procedure in which you are fixing somehow, in this case, a polynomially large insistence size number of parameters, will reproduce something like the dynamics of a quantum system in which you have an exponentially large number of fixed parameters. Okay, so, and we have an understanding of why that is. I'm not going to go into more details about that, but we understand that in as a generalized way of looking at eigenstate thermalization in integrable systems. Okay, and this is also very related to thermodynamic Bethe-Ansatz idea. So essentially, the way you can really rationalize why the GE works is like, if you think that eigenstates of integrable Hamiltonians that have similar distribution of the conserved quantities have the same essentially expectation values of the observables you are interested in. Okay, so and that I think is in the spirit of the thermodynamic Bethe-Ansatz, in which you replace the ensemble by just one state. Okay, so that was the way we understood that. So these were two things we achieved some time ago. So it's first we understand what this long time is, and we also understand why this generalized Gibbs ensemble works. Okay, so now at this point, what you could ask is, and that goes into this idea of non-interacting, how is this different from non-interacting systems? Okay, so let's take a look at what would happen with the non-interacting fermions that are underlying these hardcore bosons. Well, I mean, I don't need to do a numerical calculation to show that the time average of the one particle density matrix of the fermions is precisely the GGE density matrix. Okay, so and this is very interesting because essentially it doesn't even have finite size effects, nothing. So it's an exact statement. If you compute the time average of the fermions, it's precisely what the GGE is predicting. Okay, so in that sense you will say, well, maybe there is not that much of a difference between the fermions and these hardcore bosons. Okay, but I mean, if you look at what I was showing you before, I never talked about time average, right? I was showing as a function of time. Okay, now if you, instead of asking about the time average, if you ask what is the difference between the time evolution of that one particle density matrix and the GGE prediction, then the answer is very different. Okay, so and here what you want to calculate is just this trace distance between the GGE and the instantaneous density matrix. Okay, so this is the definition. The trace of each of these matrices is the number of particles. That's why we have to put this 1 over n. And the important thing is just that since these are non-interacting particles, these one particle sectors evolve unitarily. So essentially this trace distance is independent of time. Okay, so essentially what I'm saying is that the one particle density matrix of the non-interacting fermions just doesn't relax to the GG. Okay, and another way to put it for experiments is that you can always make a measurement of some one particle quantity in the fermions, and then it won't look like the GGE prediction. is going to be changing with time. Okay, so now let's go back to the bosons and ask how does that quantity behave in the bosons, right? And you see, I mean, what I'm having in mind is that you usually hear, okay, to talk about relaxation, we need to essentially trace out a piece of the system, maybe most of the system. And here what I'm saying is, I mean, forget about tracing out pieces of the system. Trace out n-1 particles and keep the entire system. Okay, so and the question is whether that one particle density matrix for the bosons, whether it relaxes or not to the GG prediction. Okay, so now to study that, we decided to take a look at hardcore anyons. And the reason we decided that is because hardcore anyons, they essentially allow you to go continuously from free fermions to hardcore bosons. Okay, free fermions are the limit theta 0, and then essentially hardcore boson is pi. Okay, so we have a parameter to go continuously between one and the other. Okay, so and now what we did is we did quenches. Okay, for these hardcore anyons. So and we started with a box. So we did this Duncan experiment. So we started with the box. The length was 2 times the number of particles. And then we opened it into a bigger box that had 4 times the number of particles. Okay, and then look at the dynamics. So these are the initial momentum distribution functions. So you see this looks like the fermionic distribution function you expect, and then there are the anyonic distribution function, and then the symmetrical at the end is just the hardcore boson. Okay, so we can go continuously between the two. Now, if you look at the GGE, well, for the fermions, it looks like the initial one, but you see there is this little peak, which is a reminder that this is an open box, so the conserved quantities are not the occupation of the momentum modes. So, and then it just evolved to something that is just broad. Okay, so this is the initial one, this is the GGE, and now the question is, how does one go from this to whatever the system evolves to? Okay.
Marcus, is there any problem in doing from 4n to 2n?
What do you mean? From 2n to 4n? Why? I mean, we just open the box.
Yeah, but just very simple things. Imagine you have one quantum mechanics. You have infinite box. Mm-hmm. Now, the two things are not the same, because if I enlarge the box, whatever wave function I have initially, I'm able to express in the new basis.
Right.
But it's not true the vice versa.
That's true, and that's why we go from 2n to 4n, and not vice versa. Oh, you mean what happens if we go from 4n to 2n? Then what you would have to do is just trace, and then your system would be like open.
So I have to do carefully, right?
Right, it would be a different calculation. Right? So we wanted to remain like unitary and so on. But yeah, you can cut a piece of a system, right? So what you would do is just trace out the rest, and then evolve unitarily with the, I mean, it's a mixed density matrix with the Hamiltonian of the piece that you have left. I mean, you can do it, but it's a different calculation. Okay, so now let's take a look at the dynamics, and here is where the surprises come. So we have to analyze independently the free fermionic limit and the hardcore boson. Okay, so the first thing is let's take a look at the trace distance. I mean, as I proved before, it's just constant, so nothing interesting happened. But now you want to look at observables like momentum distribution function, which are of interest to experiments, okay? And then what I'm plotting here is just the difference, you see, the integrated difference between the time evolving one and the GGE prediction. Okay, it's just a number at each time, okay? And now let's take a look at how this looks at, first, let's take a look at the initial one as a function of system size. So you see that this difference goes down. Right? It's like the initial momentum distribution function is becoming closer and closer to the GG. And this is nothing but telling you that as you increase the box size, okay, your conserved quantities are going to be the occupation of the momentum modes. Okay? But now comes the surprising thing in here. So you let the thing go, and then fermions, the momentum distribution function is not going to change until they realize that they are in a box. So they have to hit the edge. And that's this point in here that you see that the time increases with increasing system size. And at that point, they realize that they are in a box, and they start oscillating, and actually the difference between the GGE and the momentum distribution function increases. Okay? So essentially the momentum distribution starts. So what does that tell you, right? It tells you that if you do an experiment and you look at the momentum distribution function at different times, you're going to get different results, and they are going to be different from the GGE. Okay? So, and that's the way this trace distance, the fact that it's constant, can be revealed experimentally. Now you can look at something else, like the side occupations, okay? And if you look at the side occupations, well, what you see is that the difference, again, between the time evolving one and the GGE, at long times you have a lot of oscillations. It decreases with increasing system size, okay? So that's what you would say. At long time, this quantity is relaxing, while this one is not relaxing.
Why is there so many fluctuations?
It's an experimental fact. So, why there are the fluctuations? I mean, you can think of it like the GGE is just like a box up to a peak, okay? And if you look at it different time, what you will see is like spikes all over the place in that momentum distribution function. And what happens is those spikes, they move around and so on. So that's why all these things fluctuate so much. Okay, but the other thing is that you see, look, I mean, the size of the fluctuation also decreases with increasing system size. Okay, so as you go to the very large system size, it's going to become something very small. Okay, but it's only polynomially decreasing with increasing system size. Okay, and in here is the same, and this is a log-log plot, so this is decreasing a lot. Okay, and now what happens if you make this theta different from 0? Well, it doesn't matter how large you make theta. What you see is as you increase system size, at long time, this difference decrease. Okay, and this is the momentum distribution function. So I should tell you that for all anyons, the density is always the same. It's the one of non-interacting fermions. So, but the momentum distribution function does depend on theta, and it always decreases with increasing system size. Okay, and if you look at the trace distance, again, it decreases with increasing system size. Okay, so that's somehow like, I mean, that's already the first indication that the entire one particle density matrix of these hardcore anyons is relaxing to the GGE. Okay, now to make this, like to see this better, what we do is we average over the last decade here, okay, for all these quantities, and actually let's focus only on the trace distance. And then we plot it here. So that's what we call this D infinity, is that long time average at the largest time. And we can plot that as a function of theta for different system sizes. Now what you see is that as you increase system size, you see that this trace distance decreases. So for small system, it almost doesn't realize that it's moving away from the integrable point, from the non-interacting point. But as you increase the system size, you see that it's becoming sharper and sharper, right? So, I mean, what you would expect from here is that in the thermodynamic limit, it will be like just a delta function, okay? So
was theta equals to 0.123 fermions?
pardon?
Zero
Zero is fermions. Okay.
So theta equals to pi correspond to...
Is hardcore boson. That's exactly the hardcore boson point, right? And now you are also interested in how this thing is scaling with the system size. So you just take a given theta and then plot it as a function of the system size. And we have that it scales, it has a nice power law scaling, so the trace distance decreases as 1 over the square root of n. Okay, so the smaller the theta, the larger the system size that you need to start seeing the onset of that power law behavior. Okay, and I mean, essentially for the hardcore bosons is where you see it the best. And for fermions, I mean, this changes very little. It's actually going to 1/2, and this we can prove analytically that in the thermodynamic limit it should be 1/2, and indeed we see that it goes power law to 1/2. Okay, so what is it that closes what I wanted to tell you about this integrable system mappable to non-interacting one? So essentially what we find for these hardcore anyons is that so long as you have these interactions, so that this mapping is something that you need to solve the problem, the entire one particle density matrix relaxes to the GGE prediction. Now, why is this important? Because that tells us that it doesn't matter which experimental observable, like one particle experimental observable you looked at, is always going to be GGE. Okay. On the other hand, if you look at the free fermions, you may see some of them that will look like the GGE, like the density, but some others, like the momentum distribution function, that won't look like the GGE. Okay, so that tells you that interactions are important, and they are making the whole thing fundamentally different for the two systems. Okay, so questions on that part. So what I'm going to do now is just jump to really models that cannot be mapped to non-interactive. Okay. Okay. So if you have other questions, then we can discuss them later.
Marcus, I have a question actually. If I try to map anyons or Harcourt bosons to fermions, the only thing that really matters is the Jordan-Wigner string. And if I think about it in a bosonized form, carries a green function which is an exponent, actually 1/2. Is this the same 1/2 that you are getting here?
No, I mean
It's completely
it's a completely different one. Yeah.
Of course, this holds at equilibrium, what I'm saying, yeah?
Yeah, that's right.
So,
Mm-hmm.
but there is no direct relation.
No. Okay. Other questions? Okay, so I mean, yeah, here the important thing is that it's a power law decay. Okay.
Sorry, how much all this depend on dimensionality?
What do you mean dimensionality? So, I mean, this is only integrable in 1D, right? So if I go to higher dimensions, it's all dies, right? Harcourt bosons are not integrable in 2D.
You cannot map to free fermions.
You can, but you end up with, okay, not to free fermions. You can map to fermions, but you end up with interacting fermions. So all this talk to 1D. Okay.
So if I do XY model,
This is the, oh, you mean XY, not, this is XX.
okay, if it's XX, that counts as interacting in your logic, right?
Yeah.
Because I need the strings.
Right, exactly. Yeah, this is XX. Okay, so then let's move to the interacting cases, to the models that cannot be mapped, and this is like XXC and so on. Now, I mean, dealing with these systems is almost as, I mean, except for very few exceptions, as dealing with non-integrable systems, okay? So, I mean, if you want to compute correlation functions and so on in general, this is very complicated using very answers. So this is all very, I think it's very difficult. And for quenches, it's been done for very specific initial states and so on, okay? So now, let me tell you first about like a link cluster expansion approach that, I mean, we developed several years ago when we were not even thinking about these thermalization issues, okay? So it was really to do frustrating magnets, okay? Condensed matter. And it turns out that it's been very helpful to understand now quenches in integrable system, okay? So let me very quickly tell you about that. So this link cluster, numerical link cluster approach is based on a link cluster theorem. And this is what the theorem says. The theorem says it's something very generic. I mean, it doesn't have anything to do with physics. It's just extensive quantities on graphs. It tells you that if you are interested in the intensive part, so the value per site of some extensive quantity, you can always compute it as the sum overall connected cluster that you can embed it in whatever large graph you have of a multiplicity of the cluster. I'm going to tell you in a minute what this is, times the weight of the observable in that cluster. Okay, like just a theorem, and the weight of the observable in the cluster is computed using something that is called the inclusion-exclusion principle, and it tells you that all you need to do is compute have the observable in the cluster and subtract the weight of all the subclusters of that cluster that are connected. Okay, so no physics whatsoever at that point. So, and this is essentially done recursively. Right? Now, if you want to put the physics, you have to think what is the observable, and then if you have a quantum system, that would be just the trace of your observable and using the grand canonical density matrix. Okay, so this is essentially now the connection to physics. That's how you compute this O, and then you put it there and compute it. Now it turns out that if you do like a high temperature expansion, okay, of these density matrices, by doing this you end up with the traditional high temperature expansions that you learn in statistical mechanics. Okay? It's just that that you never went through the link cluster theorem to think about them. You took a system that was very large and you did the high temperature expansion. Now when we were trying at that time to think about frustrated magnets, we saw some issues with this high temperature expansion. So we went back to this cluster, link cluster theorem and said, look, I mean, how about we compute these observables exactly in each cluster and then carry out the entire program without doing any expansion. It turned out to work extremely well, and essentially this can converge even if you go to zero temperature. You have a disordered ground state. So it was a great improvement over high temperature expansions. You have something that converges up to zero temperature. Okay, so now let me, so that you understand what goes behind this, let me very quickly tell you how this is done, so that you see what. So suppose you have the square lattice and you have the Heisenberg model and you want to calculate observables there. The first thing you have to do is find, and this is in the thermodynamic limit, find all the clusters that you can embed on that square lattice. Okay, and then you start from like one side, okay, and then we have one bond. And then I was telling you this multiplicity, right? Now you can understand what this multiplicity is. In the square lattice, you can put the bond like this or like this. That's the two. And then, you know, two bonds, then you can put it like this or like this, and then now you understand what this meant. Okay, but now as physicists, we look at this and we know the Heisenberg Hamiltonian in these two clusters is the same. So we don't want to really like diagonalize it here and here. So we have to teach the computer to deal with topologies, that differentiate these guys from other ones, or this guy from this one. So, and then you group all the topological clusters. So they are all the ones with different Hamiltonians. And then you have a list, all the topological clusters, and this is the number. Okay? This is something that grows exponentially. And then the next thing that you need is you want to do this subtraction. So you have to find all the subclusters that are present in all the connected subcluster of a cluster, and then you find them. You build a table, keep it in your computer, and then you can use it for the years. Okay? And now at the time of the calculation is where the model is important. So what I'm saying is you could use this, I don't know, for Hubbard model, Heisenberg model, Bose-Hubbard model in the square lattice. Now then you have to diagonalize the clusters and then do the subtraction. Now the Heisenberg model in 2D is not frustrated, so one can actually solve it using quantum Monte Carlo, and you can study very large systems. So for these temperatures, for the purpose of this talk, you can think of this quantum Monte Carlo as just the exact solution. Okay, and now you do the calculation. I won't discuss that there is some freedom in the expansion. I was showing you before the expansion in bonds. You do the calculation, and then you do up to 12 bonds, you get some result. 13, you get some result. So what you see is that essentially up to some point, you get exact result, and then the series after that diverge, right? So as you increase the number of orders, what happens at this point is moving forward to lower and lower temperature. Okay? Now, at the time we discussed this, and I'm sorry I have to go through all the details because then you will see what the advantage is. People were saying like, well, look, how is that different from exact normalization? Ultimately, you are diagonalizing the clusters, okay? And it took us some time to really understand because even exact normalization is not that clear how things are converging to the thermodynamic limit result, okay? Now, here is something that we learned recently, is that the way different ensembles and boundary conditions approach the thermodynamic limit result is not the same. It's not always the same. Okay, so there is. I mean, usually you would say it's power law. It's something that depends on one of the inverse of the system size. But it turns out that there is one preferred ensemble, the grand canonical ensemble, and one preferred boundary condition, which is periodic boundary condition. And for those, as you increase system size, you go exponentially fast to the thermodynamic limit result. Everything else is power law. Okay, and we actually we have two proofs of this statement, which I think is very useful. It should be in the courses of statistical mechanics, because sometimes you say like, oh, if I'm going to do a calculation at finite temperature, let me do canonical because I don't have to diagonalize all sectors. Well, that's a wrong way to go about it, because you are making an error that is power law in system size. If you do grand canonical, you're going to get something that is exponential. Okay, and all you need for that is to have unordered phases, so no long range. Okay, and then that was interesting, and it also worries us because you have something that is exponential, but it turns out that NLCs are also exponential, but they are an even faster exponential. So it looks like they are probably the best we can do if you decide to diagonalize stuff. And just as an example, let me show you this: the kinetic energy for the TV model, which is nothing but XXC, is integrable. We know the exact solution as a function of L would be the order of the link cluster expansion or the size of your clusters with canonical ensemble or grand canonical. So let's take a look at this. This is canonical ensemble open, and this is semi-log. So this is a power law actually. Okay, this canonical ensemble periodic, again power law, grand canonical open, power law, grand canonical periodic, exponential. But NLCE, exponential, but a faster exponential. Okay, so essentially, at least for thermodynamic, for thermal equilibrium, this seems to be the best we can do. Okay, now the question is, what does all
But the cluster that doesn't know at all the boundary condition, right?
who which cluster?
I mean, the algorithm you put.
Oh, the link cluster. No, that's correct, because the link cluster is written in the thermodynamic.
Yeah,
limit.
exactly.
Right, exactly. So in the link cluster, there are no boundaries, right? So the link cluster is directly, I mean, it's like you are building the, I mean, you are taking out the exact contribution of each system size to the thermodynamic. Yeah, that's the essential difference with doing a finite system calculation. Okay, so but now, okay, all interesting, but what does that have to do with dynamics? Okay, so and here comes the surprising observation. So now what we can think of, remember, I mean, on this cluster, all we did is like we independently build the grand canonical ensemble for each of them. Now we can think, okay, let's have a system that is in thermal equilibrium, so, and each cluster has some density matrix. And then at the time of the quench, we are gonna disconnect that, okay, from the bath. So all the clusters are attached to a bath, and you have your, we disconnect it from the bath, okay? And then we do the dynamics of each cluster. Now, what you can do is for each cluster, well, you can write all the eigenstates of the new, of the old Hamiltonian in the new one, and you can compute the time evolution of the density matrix in each cluster. That's but you can also compute the time average of this. Okay, so you see what I'm getting. So when you do the time average, all the off-diagonal terms go away, and you end up with a density matrix, which is diagonal, as the thermal equilibrium density matrix is. But now the difference is that the weights are not thermal equilibrium weights. The weights are this beast in here. Okay? And then, I mean, yeah, this is more complicated, but it's something that the computer can do. So essentially what I'm saying is that now we can use that method to compute the very long time limit of observables after a quench. Okay, so that's essentially the statement. So it's just use this density matrix, which we call the diagonal ensemble. It's like the infinite time average, to do that link cluster expansion. Okay, so now all these, I still haven't posed what is it that I want to answer. Okay, why is it that I went through all this trouble? So this is what I want to answer. So I want to see what happens when I quench from a generic non-integrable system to an integrable one that is interacting. Okay, which you will not be able to do in general with your with variables. Okay, so that, and the question is, do these quenches lead to thermalization? Okay. Now, why is it that that question is important? I can tell you 2 reasons why this is something that's been worrying me for a while. The first one comes from ideas of typicality, right? So if you discuss with the people that have developed an intuition on dynamics and so on based on typicality, what they will tell you is like, look, whenever you are doing integrable system and you don't see thermalization, it's because you really went through humongous pain to find very special initial state. Okay, maybe a product state, maybe the ground state, and so on. But you know, whatever you perturb you do is going to lead to thermalization. That's essentially the statement that you will get. Okay, and that goes through this canonical typicality theorem that tells you that typical state, and the question is typical with respect to what, right? So these are typical state with respect to the hard measure. They have thermal reduced density. Okay, that's the statement. So, and that's why you would say like, oh, maybe if you have some non-integrable system, which is what we have around mostly, and it's in thermal equilibrium, and then you use quench to integrability, maybe it's going to look thermal. Okay, that's the problem I want to address. So now there is a different way to get to the similar conclusion, and that was actually the way I got into that question, not from the typicality point of view. And the idea is the following, okay? Suppose that you have some Hamiltonian that is non-integrable, okay? And that you can write it as an integrable Hamiltonian plus some integrability in breaking term, okay? And now suppose that you start with a thermal state or an eigenstate of that non-integrable Hamiltonian, and you quench to integrability, okay? What do you expect to happen? Well, actually, from eigenstate thermalization, what we expect is that the system will thermalize. And the reason we expect that is the following. So if you think about an observable, okay, in the integrable system, so let me just say O alpha alpha, this expectation value in the eigenstate of the integrable system as a function of E alpha. How does this look like? I mean, it's a crazy thing. Okay? That's why there is no eigenstate thermalization. That's why we need essentially a generalized Gibson sample to describe what happens. Now, this is the lambda 0, right? If you go to lambda non-zero, okay, so O alpha alpha, lambda, very small lambda non-zero, what you expect to have is a line, okay? Now, how can you get that line? For very small lambda, this line is nothing but the microcanonical prediction that you will have in the integrable limit. Okay, so what it's telling you is that each eigenstate of the non-integrable model becomes a superposition of nearby states here, just does like a random sampling and give you the microcanonical prediction. Okay, so that was the logic. So in any case, from there we saw like, okay, at least for very small lambda is guaranteed, this is going to give you thermalization. Okay, but then the question is what happens as lambda increases. So is this the problem understood? Like, so essentially what I'm saying here is that there was the potential that in general, you know, all this integrability would be irrelevant, okay, to most quenches that you could come up in the lab. So, and then, I mean,
if you increase lambda,
right,
it's not more and more non-integrable one.
Right. So,
I don't get what is the question in a way.
So the question is, you see, for a small lambda, very small lambda, I'm saying is because these matrix elements are very small, is that all you can be doing is just drawing up states from the microcanonical window and averaging over it. But as you increase lambda, you are drawing states that are further and further away. So there is potential for this argument not working. So for when you quench back to the integrable model, not having something that is the microcanonical prediction. Okay? So yeah. So the question is, what is the role of that integrability breaking term? Still not you see. Yeah.
Sorry, you're doing the vice versa.
Right, exactly. I'm doing it in the opposite direction.
Okay.
I'm using the eigenstate thermalization to argue that it will lead to thermalization.
Okay.
So and then within numerics, And indeed, I mean, we found indication of precisely this. So what we did is we took, I mean, look, there is a lot of data here. I'm just want to say, like we did for hardcore bosons and spinless fermion, the behavior is similar, so forget about this. And we did different system sizes. So we also looked at how things scale. Okay, now let's focus on one plot. So what we do is we take an eigenstate of the non-integrable Hamiltonian, this guy here, and quench to integrability, do the dynamics, compute the observable. And then we compute the difference with respect to the thermal prediction. Okay, so if you are integrable, okay, so if you are integrable, you get some difference because you just take one of these states, and then it's going to be it's going to be different from the thermal prediction. And as you increase the integrability breaking, but the system is too small, well, I mean, you still look almost like integrable, but you see the difference decrease. Okay, and then you get a minimum here, and now you see that as you increase system size, this minimum value is decreasing. So you're saying like, it looks like as you increase the system size, you are really thermalizing the difference between the dynamics and the thermal prediction decreases. But then it went up, and sometimes it stayed flat, but this value also decreased with increasing system size. So I can tell you that at this time, we were really thinking that, or at least I was really thinking that you will in general get thermalization. Okay? Quenching from non-integrable to integrable. And the way you can rationalize that is that, okay, maybe then when you quench to integrability, you have a random sampling of whatever the microcanonical will be. Okay?
I mean, I don't know.
Okay, right, but that's what I want to answer, right? That's what I want to answer.
Let me argue differently.
Okay, good. That's
I think depends strongly on the initial states.
No. Oh, okay. So this initial state was an eigenstate of the non-integrable Hamiltonian, and within a given window, they are all very similar.
I mean, imagine you have states which are. I mean, you can cook states which.
Oh, no,
what you
right.
say will work. But
No, right.
Let me take a generic states.
Oh,
So
then we have to discuss what you mean by generic,
Okay,
right?
so I take a states. In any case, in the integrable theory, I have a basis,
Right.
which are eigenvector of all the charges.
Mm-hmm.
So on these states, I can compute the average of these charges.
Yeah.
And turns out to be constant,
Mm-hmm.
right? Because it's what the evolution of integrable model are.
Mm-hmm.
So I will have evolution supported by an infinite number of conservation laws.
Mm-hmm.
Now, according to all the dictionary, this is not thermal. Namely, I can always, unless you choose a state where all these charges has very, very small value, so that you are full to be thermal, they are not thermal. I don't
No,
see how
but what is the initial state there?
But whatever it is, it will have some expectation value.
Right. But I
Means it
mean,
will preserve forever.
that will be preserved. But the question is, why are you sure that the initial states will not have the distribution of conserved quantities of your system after the quench? As a matter of fact, I am arguing that from ETH, that's going to be precisely the case when lambda is very small. It's guaranteed because of precisely what I was telling you. You see, it's guaranteed that this eigenstate has the thermal distribution of the conserved quantities of this system in here. Okay? I agree. It depends on the initial state, but I'm just saying that by this construction, you are making sure that that happens. So the question is, as you increase lambda, which is, this is not guaranteed anymore, now, will you randomly sample these states such that you remain with the thermal distribution of the conserved quantities or not?
And also,
That's
I think depend very much to which term of what is the term that is breaking integrability, alias if it is adiabatic with the spectrum of the integrable one or not. This changes completely the story.
What do you mean by adiabatic? So let's take a look at what I'm going to do. What I'm going to do is I'm going to study the XXC, quenches to the XXC, and the way I'm going to break integrability is by adding next nearest neighbor interactions. Okay?
So the adiabatic means the spectrum changing lambda, vary continuously
Continuously
lambda,
between.
or there is a jump. I mean, there is
I think, yeah, in this case, I think it's going to be continuously.
change. The story changed a lot.
But I mean, you will like the answer anyway for this one that maybe is the one that you like the least because of this continuity. Okay, so we are going to study these quenches. And now the good thing is that we have that approach that is very accurate, okay? So, and then we are going to look at different observables, like entropy per site, interaction energy, momentum distribution functions. Okay, so let's do the quenches and see what happens. Okay. The first thing is I just do the quench, compute the entropy of the grand canonical ensemble, the entropy of that infinite time average of the diagonal ensemble, and I just plot that as a function of the order of this diagonal ensemble for a fixed grand canonical ensemble. It's just that the best I can do is 18 sites. Okay, we can take the 18 sites prediction for that temperature, the initial temperature, to be the exact result. Okay, it's converged within the machine precision. And now let's see what happens for different values of that lambda. So lambda 0 is no quench. And what you get is just that this difference just goes exponentially to 0, which was what I was claiming before, that convergence is exponential. There is no quench. But you see, as soon as you put a quench, a small value of lambda, you see that it goes to 0 up to some point, and then it becomes a very small value. And as you increase the magnitude of gamma, you see that that becomes larger and larger. Okay? So what is it that we learned from here? Is that essentially after the quench, now the number of states that are involved in the dynamic is much smaller, actually exponentially smaller than the number of thermal states. Okay? Because remember, the entropy is the log of the number of states, so a finite difference between the logs tells you an exponential difference between the numbers. Okay? And then what you can do is now plot this, which I would claim is the thermodynamic limit result, as a function of lambda. Okay? And okay, you get some curve and you can plot it for different temperatures. Now, this line in here is not a line going through the data point. That's a feed to a power. Okay? Now, can you guess what power that is? So we can actually figure out what that power is just by analyzing what's happening in here. Let's take a look at this. You can expand both the diagonal ensemble and grand canonical ensemble in powers of lambda. It's a small parameter. You have the 0th term, which is the same for the two, because there is no quench. The first term, the second term, and so on. But now you see, the diagonal ensemble entropy cannot be larger than the grand canonical ensemble one. Okay? Why is it that it cannot be larger? Because the grand canonical is the maximal entropy. So if it's going to be different, it can only be smaller. Okay? So you immediately see, since it has to be smaller, it cannot depend on lambda, because lambda can be plus or minus. So the contribution, when you do the difference of the first term, has to go away. So it can only depend on lambda squared. Well, that power is precisely 2. Okay? So somehow it's telling you that, this may be the thermodynamic limit result in which you see that this changes with lambda squared. Okay, so that's the first piece of information that we learn, is that now there are exponentially less states involved in the dynamics than in the thermal equilibrium relation. Okay, that's going in the right direction, but that doesn't tell us whether you are sampling those states randomly. And then you can do just the calculation of the interaction energy and compute the difference between the thermal and the diagonal ensemble. And this is what is shown in here, again, as a function of the order. You see it's flat, and you plot it as a function of lambda, and you get now again a power law. This power, again, is not a line through the point, it's a feed to a power. This power, we can also get analytically, right? Just doing the same argument, except that now we don't have any maximal statement to make, so it can be linear. And this is precisely what you see here, it's linear. And you can see this for different observables. So the same you see for the momentum distribution function. So in any case,
What happened if you increase lambda?
pardon?
What happened if you increase lambda?
Lambda, larger lambda here? Yeah, I mean, it deviates. At some point, it deviates. So if lambda is too large, yeah, it deviates a lot from that small lambda. But okay, so what is it that I have learned here? Okay, you see, even though that argument for very small lambda still works, you see the difference is going to go to 0. as you depart from the integrable point, what you see is that the difference becomes non-zero. Okay, it just tells you that even if you start with thermal states of this non-integrable system and quench to integrability, you just don't thermalize. Okay, so which goes with precisely your intuition, but goes against this typicality thinking that that you have to work extremely hard to see something non-thermal. Well, I think for experiments, this is the simplest thing: get something thermal from a non-integrable system, that's equilibrium. Quench to integrability, they are not going to see thermalization. Okay. So with that, I'm going to just finish. So this is the summary. What have I argued? So I first discussed these quenches from integrable models that are mappable to non-interacting ones. And there I argue that the one particle density matrix of the model that does have interaction relaxes to the GGE prediction, and that interactions there play a crucial role. So they are the ones that allow that to occur. If you don't have interactions, then there is no relaxation. And the important thing here is that the relaxation to that GGE occurs without having to trace out a spatial domain. So all you are tracing out is n-1 degrees of freedom. So the second part, I argue that quenches from non-integrable systems to integrable systems are very different from quenches between non-integrable systems. Okay? The first thing I show you is that the diagonal entropy after the quench is always smaller than the thermal one, so that energy distributions after the quench are very sparse. This in general doesn't happen when you quench to non-integrable systems. And the observables do not thermalize, and that is telling you that essentially you are not randomly sampling this, the eigenstates in the microcanonical window, so that this lack of thermalization is robust at integrability. So with that, let me thank my collaborators, the support here, and thank you for your attention.
Other questions?
Just non-typicality as a concept of an integral model, you should have quenched in the other way. Starting from an integrable to a non-integrable.
Then you always thermalize. It doesn't matter.
So this means that the eigenset of an integrable system are also typical.
They
They are not so atypical.
What do you mean? No,
is with respect to
Yeah,
Right.
The statement of typicality is that if you take typical state with respect to the R measure, then
Right.
the reduced density matrix will become one. So here I pick as a state the eigenset of an integrable Hamiltonian and thermalize. So it's not so much atypical.
No, right, no, okay, so no, but you have to be very careful, because the question is, why does it thermalize? Okay, and that goes through this eigenstate thermalization hypothesis. And you see, these typicality arguments, they never discuss what the difference between integrable and non-integrable systems are. And what I'm saying is that when you go and quench to a non-integrable model, then this typicality argument plays no role, because eigenstate thermalization ensures that you will always thermalize. It doesn't matter what the initial state is. Okay, so it has nothing to do with typicality in that sense. So that's why the reverse quench will always thermalize simply because of eigenstate thermalization. Then we don't need to talk about typicality in this. The other quench then is more complicated. Then we need to, from going to an integrable model, because there we know that there is no eigenstate thermalization hypothesis. So then the question is, are you randomly sampling the microcanonical window? And the answer is no. Right. So in a sense, this is like saying typicality is useless. So, but,
Is it really surprising, very surprising that you don't thermalize in an integrable system? For somebody who doesn't know much like me, it's not really surprising.
right. But
Yeah.
I would agree with that.
So
Yeah.
value free charges. So.
Right. But yeah, when you develop an intuition from like a typicality, you find it very surprising. I'm still arguing with many people about that. So
Yeah, but you have to conciliate with conservation quantities, which are
that's true.
hidden-
It's infinite
which
of
are-
them.
Yeah, which is hidden in this huge ocean of hyperspace, but
Right.
they are
Right.
there.
But you see that I do have a protocol
Uh-huh.
to manage to do that. It's just take the eigenstate of a non-integrable model with a very small integrability breaking perturbation. I will ensure that when I quench to the integrable point, I will thermalize. Okay, because those eigenstates are really superpositions of the eigenstate of the integrable system in the microcanonical ring. Right.
Well,
Well, I was just trying to understand if the kind of work by Cardi and Calabrese was also another example of this, right? So you quench to a critical point, so that's integrable and not
Right.
generically free. And they started out by constructing initial states that they obtained by perturbing their CFT states.
Yeah.
So in a sense, you might regard for some parameters they're not ground states of integrable systems,
Right.
but probably ground states.
And they did
and
thermalize.
they did them.
Right, so that's
more
it.
generally
They don't.
found that they don't.
So you're totally right. So that's why all these arguments are very tricky, right? Because there are actually exact solutions, and that was that first paper by Calabrese and Cardi, and those initial states did thermalize, and they were CFTs actually. So it's yeah. So it's not that it's a tricky question. So
Thermalize with generalized temperature.
no, with final temperature.
No. I mean, in the GG sense.
No,
No,
in the
their
thermal
first
sense.
paper, there wasn't a GGE, so they constructed their initial state
Yeah.
in a particular way by
You can always cook states that looks thermal. I mean, this is
No,
the
but that's
point.
somehow the idea, right? So he's saying, what happens if you go to a generic interacting integrable problem? And so there's
Yeah.
a question of your state preparation.
Right.
And do you thermalize or not? So somehow it's a question of state preparation, right? So the dynamics is kind of given.
Yeah.
And so in their original paper, my understanding is that they thermalized because of the particular way they built
Okay,
their
yeah,
initial
yeah,
states.
yeah.
But nonetheless, if you look at generic ways to build
Look,
initial
let me
states, you
put
tend
differently.
to GG.
Imagine I take an initial state where all the expectation of the charges are 0.
Right, but
Or
you have, but
there is more.
you have to
It's a
think.
subset of
No,
the
but
GG.
Giuseppe, you have to think about this from the point of view of an experimentalist. I mean, the experimentalist cannot come and say like, "Oh, I'm going to put the charge that I want,"
No,
right?
It looks vice versa. I mean,
Right.
vice versa.
Right.
I know it's very complicated.
Yeah.
Yes.
So they just have some initial state, and then
Other questions? I'm late in question. Thermalize or not thermalize? This is the problem. Okay, if not, I would like just to remind that today we have an additional seminar this afternoon, 4 o'clock, which is not going to be here, but in the